Okay, hello everyone, it's Sadar, and we are in part 23 from our tutorial, a tutorial to writing a real-time operating system. In previous part, I talked about turning on an LED with assembly instructions and assembly programming, and I talked about conditional branch instructions. Okay, but in this part, I want to talk about pre-index and post-index memory access. Okay, memory access, LDR or STR. Okay, and after that I want to talk about conditional instructions. As I said in previous parts, I said that you can have conditional branch like branch equal, branch if z in APSR is 1. Okay, but in ARM assembly programming you can have conditional instructions, okay, with add some suffixes after of your instructions. For example, add not equal. Okay, you can have conditional instructions in assembly programming. And after that, our topic is test branch. I want to talk about test branch and TBB instruction. With this instruction, you can easily implement switch block in C programming. Okay, switch and case blocks in C programming. Okay, table branch. So let's get down to our business. Okay, first I want to talk about pre-index memory access, ordinary access. All of our accesses in memory was pre-index memory access. What's pre-index memory access? In pre-index memory access you have a base address and an offset, register offset or constant offset. Okay, in this way you can store and load some value to memory and in your register. Okay, in this way your base address plus your offset is your complete address, and you can load a value from this address to your register or from your register to memory. Okay, with a store instruction. It's pre-index memory access. Okay, because before to access to memory you should add your offset with your base address. Okay, but let's give you an example for pre-index memory access. Assume that you want to implement this C programming block in assembly programming. As you can see, I have an array of bytes. uint8 is byte in C programming, and size of my array is 100 in hexadecimal from 0 to 0xff. Size of my array is 0x100. It's equal to 256 in decimal. Okay, it's size of my array, and I want to write index of array in each byte. Okay, so my array will be 0 1 2 3 4 2 0xff, hexadecimal numbers. Okay, here is my array, but this for block in C programming is literally similar to this while block. Okay, first my index is 0, I equal to 0, and maximum value of my index is 0xff. Okay, for those index that are smaller and equal to 0xff. Okay, like this. Write your value to your array, and after that I plus plus. Okay, this block is completely like this while block. This for block is completely like this while block in C programming. But how can I implement my block and my loop in assembly programming? Here, for example, assume that R1 is index. Okay, R1 is I, okay, and first value of I is 0, R1 is 0, okay, and here is first address of my array, okay, it's address of first byte in my array, address of first byte in my array, okay, and I want to write 0 to FF in my array. First I need a loop. Here is my loop, okay, and branch to loop, okay, here is my loop, and I need a conditional branch to implement my loop. But before conditional branch, I need update flagger instructions, okay. First, compare your index with FF, okay, compare your index with FF. If your index is greater than FF, close from loop, okay, get out of your loop, go to exit, okay. Otherwise, do codes in your loop, okay, store a value in your array, okay, store a value in your array, and I plus plus, okay, add your index plus 1, I plus plus, and in this instruction you can write the value to address of your array. R2 is at the start of your array, and R1 is index of your array, okay, and you can write your index in your array, okay. But let's run this code in my board and see the result. Okay, here I'm in debug perspective and I'm in first line of my code, and I want to run my code and write some value in array. But before that, let's see my array in memory, okay. Open your memory viewer and see your array in your memory, okay. All of bytes in my array are 0, but let's run my code and see the results. Set a breakpoint in this line 16, and run your code. Okay, now as you can see, all of value have been written in my array, okay. 0, 1, 2, 3, 4, 5, 6, and let's see the end of array, for example F0, okay, and here FF is end of my array, okay. FD in FD, FE in FE, and FF in FF, and other bytes are 0, okay. In this way you can write a value in your array, okay. But let's stop debugging, and let's get familiar with a beautiful tools and useful tools in GDB, okay. Watch point in GDB. What's watch point? With watch point you can have a better inspect on your code and on your memory in debugging, okay. But how you can set a watch point in your code? With watch and, for example, your variable name, for example watch and name of your variable foo, or for example var1, okay. In this way you can set a watch point for foo or var1, okay. But when you set a watch point in your variable, your processor will break when your processor write a value to your variable, okay. Break when write to variable. When you write rwatch and your variable, your processor will break when you read from your variable, okay, in your code. And when you write a watch, your processor will break when read and write, okay, read from your variable and write to your variable. But for assembly programming, if you want to set a watch point on an address, you can use watch star and your address. But it's better to give the size of your memory that you want to set a breakpoint on that. For example, if you want to set a breakpoint on a byte, you can use char star. Okay, you can use typecasting to set a breakpoint in a byte. If you want to set a breakpoint in a half word, you can use short int. Okay, if you want to set a breakpoint of word or 4 byte, you can use int star. Okay, cast to int star. In this way, you can set a breakpoint on your memory space. Okay, but let's see the watch point in Eclipse. But before to debug my project, let's add a line to my code. What's that? Read from this address. Okay, load or read from this address. Why I need to add this line to my code? Because this line creates a delay after a store. Okay, and it can help my processor and my debugger to have a better debugging. Okay, it just creates a load, it just creates a delay after this access to this, after this access to memory. Okay, let's debug my project. First build that. And debug your project. Okay, now I'm in debug perspective, and if you want to add a debug, if you want to add a watch point in your on your memory, first open debug console. Here is debug console, and set your watch point. To add a watch point, write watch star, because I want to set a watch point on an address. I want to add a set of watch point for a byte, char star, and my address. For example, 0x200001F0 FE, for example. Okay, I want to add a watch point to this address. Press enter. Now I have a watch point in this address. So let's run my code and see memory. Okay, I've added watch point to this address. Okay, now let's run my code. Now, as you can see, your processor will stop after writing a value to this address and does not write value in FF. Okay, stop after writing a value to this address because I have a watch point in this address. But let's inspect my program. As I said, R1 is my index. Okay, now my index is FE. Okay, so let's run my code. Another time, branch in the first of your loop, compare your index is 255 with FF. My index is equal to FF, and another time run your loop, write a value to your array, and another time compare your index with FF. Okay, but in this time my index is greater than FF. Okay, so branch if greater than. Now get out of my loop, exit from my loop. Okay, I'm in operation. Branch to exit. Okay, in this way I can implement and loop in assembly programming. But let's do another time. See memory viewer. There is another way to add a watch point on your memory. Right click on address in memory and add watch point. Okay, watch point right, and range is 1 byte, okay, to this address. If you apply, now I have another watch point in 1F4. Okay, in this way. Another way, you can set a watch point in Eclipse. Okay, but let's do back to slides. Okay, now I said that I want to talk about post-index memory access. What's post-index memory access? In post-index memory access, you have constant offset. Okay, you have a constant offset and is out of this bracket. Okay, but what's differences between pre-index and post-index? When you use post-index, you can load just by base address or store just by base address, and after access to memory, your processor will change your base address. Okay, first load from this address, and after that change your base address and add the offset with your base address. Okay, post indexing. But let's do another time implement this block with, in this time, post indexing. Okay, as you can see here, my index, my first address of my array, compare with FF branch, conditional branch instruction, but in this time your base address and post index offset. But here, after memory access, your processor will change your base address. Okay, your processor will change your base address. Let's see the result in Eclipse. Okay, here is my code, and let's run that. Run to store. As you can see, R2, my base address, is this value. But let's do run this instruction, post index memory access. As you can see, my address has been changed. Okay, my address is changed with post index. Okay, but let's do run my code until end and see memory. Another time, I have written all of my value in my array. Okay, just like pre-index memory access. Okay, this was about pre-index and post-index and their differences. So let's do back to our slides and talk about conditional instructions. Okay, what's conditional instructions? As I said in previous part, you can have conditional branch equal branch if z equal to 1 in a PSR register. Okay, but you can have conditional instructions. For example, add not equal. Okay, sorry, it means add if z is 0. Okay, z is 0. You can have add not equal, for example, sub equal, conditional memory access, and other things. But if you want to use conditional instructions, you need if then block. Okay, if then block. What's if then block? If then block is the instruction IT and condition and your instruction. Okay, if you want to have a conditional instruction, you need to have a IT block before your instruction. Now this instruction is conditional instruction. Like here, compare R0 and R1, and if then block, condition is not equal, suffix, for example, not equal, equal, less than, and other suffixes. Okay, and your instruction. Now this instruction is in this block. Okay, is in this block, and here I have a conditional instruction. If you want to use IT instruction in your program, you need to write your program in UAL form. Okay, you need to add dot syntax unified before of your code. Okay, so here I can have a conditional instruction. As I said, this instruction which is after IT is a conditional instruction, and you can't put conditional instruction out of IT block. Okay, you can't ignore this instruction in your code. You need to add IT before your instruction, and you need to introduce your symbol to IT block here. Okay, now I can use add not equal in my code. Okay, but in this way I have just one instruction in my block. How can I have more instruction in my IT block with, for example, ITT or ITE? But what's the difference between ITT and ITE? As you can see, like before, I have a flag updater, I have a if then block instruction, but in this time ITT and a suffix. Okay, but in this time, because here I have a T, this suffix should be NE. Okay, and this suffix should be NE. Okay, for example, here first compare R0 and R1, and if R0 is not equal with R1, your processor will run these two instructions. But assume that you have an ITE. It means if then else. Okay, for second instruction you should have reverse type of this suffix. Okay, this suffix is not equal, reverse types of this suffix is equal. Okay, in this table I have all of reverse conditions. For example, for equal is not equal, or for not equal is equal, or for greater and equal is less than, or for less than is greater and equal. Okay, this is all of condition and a reverse form of conditions. Okay, but in this way you can implement an if then else instruction with two instruction. Okay, it means first compare R0 and R1, if not equal add, if they are equal do sub. Okay, NE T NE NE E equal reverse value. Okay, because I have an E here, but overall form of if then blocks are here. For example, if you just need one instruction, you can use IT. If you need to have two instruction in your block, you can have ITT or ITE. Okay, you can't have, for example, IET or IEE. Okay, IT, your instruction start with IT. Okay, here is false. If you want to have three instruction in your block, for example, you can have ITET. Okay, and maximum number of instruction in a block is 4 instruction. Okay, for example, here ITTEE, or for example ITETT. Okay, and IT with 3 TE or TE. Okay, For example, here I have a for instruction if then block. My suffix is not equal for t, but here is equal for e. Okay, because for e instructions, for else instructions, you need reverse condition. Okay, for example, here your processor first compare R0 with R1. If R0 is not equal with R1, add R4 with R0 and put the value in R2 and write the value of R2 in memory. Okay, but if R0 is equal with R1, first sub these two values and put in R2 and write R2 in memory. Okay, in this way you can have conditional instructions. You can't write your conditional instructions without if then block. Okay, here is if then block and conditional instructions in assembly programming. But after that, let's talk about table branch, TBB instructions and TBH instructions for byte and half word. Okay, this B means byte, this H means half word. If you want, for example, implement this switch block in assembly programming, you can use table branch and table branch instruction in assembly programming. Okay, let's give you an example. Here I have TBB instructions. You need to register PC and R0. Let's describe this instruction and this code. What does this instruction in your code? With this instruction, your program, your code will branch to this address, PC plus 4 plus 2 multiplied by value n. So what's PC, 4 and value n? PC is address of this instruction. Okay, address of this instruction is PC in memory. What's for? As I said before, it's for pipeline structure of your processor. Okay, what's value n? Value n is here. For example, value 0, assume that n is 0 and r is 0. Okay, put n in r and r is 0. Value 0 is first byte in your memory after this address. Branch table is a symbol and is the address in your memory. Okay, start of this block. Okay, here is address in your memory. So, or for example, value 1, assume that n equal to 1. Okay, is second byte after this instruction. Okay, value 0 is first byte, value 1 is second byte, and value, for example, 2 is third byte, and so on. Okay, but for example, assume that n is 1 and I want to run my code. When your processor want to run this instruction, branch to, as I said, PC plus 4 plus 2 multiplied by value 1. Value 1 is here. Destination 0. Destination 0 is this address in your memory. Branch table minus. Branch table is this address in your memory divided by 2. Let's simplify this equation. Simplify 2 by 2. But PC plus 4 is equal to this branch table address, this branch table symbol. Okay, PC plus 4, because TBB instruction, table branch instruction, is a 4-byte instruction, and PC is address of TBB, this instruction. So PC plus 4 is address of this symbol, this branch table. Okay, so you can simplify PC+4 with branch table. So your processor will branch to destination 0 to this address. So when n is 0, when n is 1, sorry, for value 1 is here destination 1, okay, destination 1. For value 1 here is destination 1. So your processor will branch to destination 1, for n equal to 1, okay, for n equal to 1. And in this way you can implement your switch case. With setting the n value, you can jump to one of these cases, one of these addresses. Okay, here with table branch I can implement a switch case, but let's see this code in Eclipse. Okay, here is my code, and let's run my code. First, register 0 is 0, okay, and I want to run table branch instruction because register R0 is 0. Your code will branch to destination 1. Okay, your code will branch to destination 0 and run your code and break, and then break from your loop. Okay, here in this way you can implement a switch case block in assembly programming in ARM architecture. Okay, let's go back to our slides. Here, branch to here is like break. Okay, but let's clear this screen. Okay, but as you can see, I have bytes in my table. Okay, so maximum value of a byte in your memory is 256. So maximum value of this equation is 256. Let's run that. For example, destination n minus branch table divided by 2, the maximum value is 256. So destination n minus branch table is 512. So maximum distances between destination n and branch table address is 512. For example, assume here destination n. Okay, maximum space for these bytes and these instructions are 512 bytes. Okay, if you want to have much bigger space for your table and your instructions and your switch case statements, you can use table branch half-word. Okay, so the value here is half-word. Okay, but if you want to study about table branch half-word, you can refer to architecture reference manual, or you can study about that on the internet. I don't want to talk about that in this part. Okay, you can study that by yourself about table branch half-word. It's just like table branch byte, but here the value of these equations, the maximum value are 2 to the power of 16. Okay, for table branch half-word, and you can have much more bigger space than this value. Okay, here was some other instructions in assembly programming about pre-index and post-index memory access, conditional instructions, if-then block, and table branch. Thank you very much to see me. enough for today, and I will see you in the next part. Thank you very much.